Hi, my name is Georgi Raduv, and I would like to present to you in this video the fully differential two-stage operational transconductors amplifier with output common mode feedback, which we can tune to a desirable level. In this video, I'll cover how to get high gain, high bandwidth, and tunable common mode output signal. So this is the architecture of a two-stage amplifier that I will discuss. The input is differential and AC coupled. So the input comes from here, and then the first stage is composed by these pseudo-differential self-biased inverters. So they amplify somewhat the signal, and they are also self-biased. So they operate in almost optimal operation mode. Just to recap, if this is the input and this is the output of the amplifier, the transfer characteristic is like this, and the transfer characteristic of the inverter is this, and this is the optimal operation point where the gain or the slope of the transfer of the signal is the highest. So we amplify then the AC component of the signal somewhat here, and it's about 30 dB, for example, because this is as demonstrated in my previous videos, about the optimum of this technology. Then I have in the second stage a common source amplifier, a differential, fully differential common source amplifier composed by this transistor for one side and this transistor for the other side. So they're in common source configuration, and they are loaded with pmos transistors. So these transistors that operate as current source loads. Now we sense the common mode of the signal with these resistors. This architecture is defined for operation with differential signals. However, the real voltage signals have always differential components and single-ended component, or the common mode component. Here, the differential components are demonstrated. We get two signals which are in 180 degrees phase rotated. So if one is increasing, then the other will be decreasing. Only the difference between these two is defined as our signal. So if this signal, say for example, is increasing, then this will be decreasing. And this is the first stage. And then we have again an inversion in the second stage, which means that this signal is increasing. So for the other signal on the other end, this is decreasing, and this will be increasing, and this will be largely decreasing. Of course, we deal with a fully balanced differential architecture, so the left and the right part are the same, which means that the response that I have at the output will be the same in magnitude but opposite in the polarity, 180 degrees phase rotation. So as much this increases then this will be decreasing, which means that at this point here will be exactly in the middle and will not change. So for differential signals, I don't have any change in this node, which is called sense common mode. So sense common mode. Now you see that for common mode signals, let's take another. No, so basically common mode disturbance, say for example, if this is increasing and this is increasing, then this will be increasing. And if this is a disturbance, if this increases, this node here will increase here, because this is a positive input, so there will be a positive difference here at the input, which means amplified positive difference, and will be fed to the gates of the current source loads. This will actually reduce the source gate voltage, and as the source gate voltage reduces, then this node will go back downwards, because then this current will reduce, this current remains the same, hence this voltage needs to change, and this voltage needs to change to stabilize the common mode. So if I look at the output, let's take one color, in time domain, what I see for this signal and this signal, these are the output signals, is first that I have a common mode component. So if I have no voltage, if I have no signal, the voltage at the output will be set to a certain common mode level. And I want to be able to control this level, because I want my transistors at the output, this transistor, the load transistor, and the amplifying GM transistor at the input, to be at the proper operation mode biased properly. And if my PVT changes, if the manufacturing technology has certain tolerances, I want to be able to still set from outside the transistors in the right operation mode through controlling the common mode of the signal. So this is this signal, the common mode. Now on top of that, I will have my differential signal, which is the red one, which will change like this, one on the end, and like this, the other end. And because this node for the differential signals is in the middle, it will not change. So here this node is sensitive only for the common mode components of the signal. Now if I want, for example, to change the common mode, let's take this. So I say this is at now 0.5, but I set it to 0.4 volts. So what will happen? This is initially 0.5 volts, 0.5 volts. Now I change here in the common mode to 0.4 volts. So there is a positive delta, which is amplified by the gain of this stage. to A times delta, and will lead to highering this voltage. And as this voltage higher, then this source gate voltage that I have here in the current sources will get smaller. As this gets smaller, this current reduces. This current in the nmos is just constant, so we don't change it. This is just what these nodes are. And this means that as the pmos current reduces, this means that this common mode needs to go downwards because the current is the same. So basically this will go to 0.4 volts. As I go to 0.4 volts here, then delta will become eventually 0, and then this node here will not need to change anymore. It will be stabilized, setting a gate voltage which sets the source gate voltage that produces certain current in the pmos transistor such that the common mode is at 0.4 volts, which I set. I can change this to 0.5, 0.6, and then the feedback will adjust the gate of the pmos transistors to the appropriate levels. So basically here I will get, for example, the common mode 0.4 volts, and on top of that I'll have my output. Now the question is, of course, what is the maximum range that I can control my common mode, and does it change the behavior of the circuit, influences the gain, etc. Of course, this signal needs to be at certain common mode level. So basically here and here we need to position certain biasing voltage or common mode of the signal. In other words, this node and this node, if we consider the voltage level, they have to be at a common mode level, and then on top of that we will have one signal and then the other signal. So this is the common mode level, and we want to have control over it and set it manually to the desired level, or at least have it in such a way that the structure at the output is properly biased, so that we get the maximum out of the gain, the maximum gain out of this structure. Here I demonstrate how we can tune the common mode. For example, because we want to set the proper level for the next stage. Now, to do this, we have to first sense the common mode, and we sense the common mode with these resistors, this resistor and this resistor. Now, see, for the differential signal, this node does not change, because if this signal changes upwards, this will change downwards for the differential component, and this node will be exactly in the middle and it will not change. So then this node is not sensitive for the differential component. However, it is sensitive to the common mode component, because the common mode component will be common for both ends of the differential output. And this means that it will be at this level. And if the common mode changes, for example, this goes up and this goes up for the common mode portion of the output voltage, then this will also go up. So then here with these two resistors, these which have equal value, we sense the common mode. Now this is fed to an amplifier, the positive end, and at the negative end of this amplifier will set the desired level of the common mode of this level here. And the output of the amplifier is fed to the gates of the current source loads of the second stage amplifier. So for example, say we bias this to a proper level. Say we want it, say it's 0.5 volts, for example, if the power supply is 1 volt. But now I want to set it to 0.6 volts, for example. So what will happen then in this feedback? If the common mode is a different level, for example 0.5, I'll have here 0.5. So this means that I'll have here a difference of minus 0.1, and this will be amplified, which means with certain gain, which means that this level will go down with certain delta depending on the gain, so 8 times 0.1. So this will go down. As this goes down, this node here will go down with this delta, which increases the source gate of this load current sources of the pmos transistors, this transistor and this transistor, and they will source more current. As they source more current, then this node will go upwards, and this will go upwards because then this current will be more than this current, which is for the nmos transistor. So basically you can also imagine that the on resistance of these current sources reduces, and hence if you imagine the pmos transistor and the nmos transistor as sort of a resistive divider of the voltage, then the voltage in the middle will go upwards. As the voltage go upwards, of course, this node here in the middle will approach 0.6, and as it approaches 0.6, then this will settle to a certain value and will no longer need to change, and then this node will set the proper source gate voltage of the pmos transistor, so that this node here in the middle is 0.6 volts, which means that then the common mode of the output signal will be 0.6 volts. At a certain moment, if we want to go to 0.5 volt, the mechanism repeats and the output voltage sets to the desired level. In this way, we can set the common mode of the signal, and we can move it to upwards or downwards to the respective level that we want. The other components of this architecture is the Miller capacitance, resistor, and so the Miller compensation, resistor, and a capacitor for the left and for the right side of the fully differential OTA. Next step is to see how we design. So all these components that we will see now, we will also show in cadence and in transistor level design. This is the transistor level implementation. So let's see what we have here. Now this is the input signal, which we will use for AC and transient analysis. For the AC simulation, the amplitude does not really matter. 1 volt is a convenient voltage, and the amplitude does not matter because AC simulation is a linearized simulation. So the AC magnitude is something relative. Then for the transient simulation, we have 100 microvolt amplitude of sine wave tone with 10 megahertz frequency. Then we have certain output resistance, 50 ohm here, 50 ohm there, and it is AC coupled to the input. Here is the first stage of the self-biased inverters. The design is simple, and it is demonstrated in our previous videos. So this will be then the input V in positive and V in negative. Then we have the amplification of the first stage, and the signal appears at these intermediate nodes. The signal then goes to the second stage, which is an nmos common source amplifier with current source pmos load, which is controlled by a common mode feedback. You can see that with Miller compensation based on capacitor and resistor, we can bypass the second stage at high frequency, and with the R we can tune the transmission 0. This will be the output, the positive and the negative output, and we have certain capacitance for the output load. Then with these resistors, two resistors will sense the common mode component of the output signal. So it's you can see that these are quite large resistors of 50 kilo ohm. Now as we sense it, this node will go to a common to a current mirror OTA, which has differential input and single-ended output. The design of the current mirror OTA is covered in our previous videos, but basically it is a version of this one. So this will be the inverting input, where we put the common mode we want to set at the output of our differential amplifier, and this the non-inverting input will be for the for sensing of the common mode of our amplifier. So this is the architecture, and let's see what are the parameters of the transistor. So everything is parameterized. So we have here the length, the unit W, and we have the fingers. And the sizes of the transistors are really like the sizes that I used in my previous videos. Now, for the common mode feedback OTA, what I did is that I reduced the L by half. The reason to do this is that it creates a pause for the common mode for the common mode, and these can influence our stability. So to make sure that I don't have to deal with stability coming via the amplifier of the common mode feedback, I make it with at least twice shorter lengths. This will reduce its gain, but I don't have very high requirements for the gain of the amplifier in the common mode feedback. If the gain is not very high enough, there will be a slight offset between the real common mode and the common mode set, which can be compensated by here setting of our common mode. So let's see how this operates. Let's first run DC simulation. The important values here are that the common mode at the moment is set to 0.5 volts. So let me then run DC simulation to see the operation mode. So I go to tools, to simulation, then results, annotate. So I have to save it and then run it. Then results, tools, results, annotate DC node voltages and operating points, and then I have the node voltages and the operating points of the transistors. So let's quickly review the most important things, and this is the common mode. So now common mode is at almost 0.5 volts. So there is a small error due to the gain of the amplifier in the common mode feedback. So see here, I set it to 500 millivolts, and a voltage is set here, which sets the common mode to almost 0.5 volts. Then, for example, let's change this. Say I want to another common mode, 600. If I run it, it is adjusted. So 600 comes here, 600. Now, if you want that this number, what you set, is closer to what you get, then you have to work with the gain of the common mode feedback OTA. So let's see if it works the other way around. So for 400 you run it. Here is 400 and it's set to almost 400, 5 millivolts error. Of course, now I can account for this and I can check it here. Alright, so let's go to the nominal, which is half of the power supply. Alright, so this is now 0.5 volts I'm setting, and I'm sensing 499.5 millivolts. Very well. Then quickly looking at the current, so these transistors are in saturation and this is in saturation, everything should operate properly. Now the next thing that we can look at is the AC simulation, and for this we can look at the body plots. So here is our definition of the amplitude body plot. We'll look at the output divided by what we get in the input, whereas the input is defined differentially as the difference of these two nodes, and the output is defined differentially as the difference of these two nodes. So this is the differential transfer. And similarly for the phase. Okay, so let's simulate. And here it is. So this is the body plot. We have a gain of 55 dB, and then it reduces as the frequency gets higher. And this is the phase characteristic. Now let's see, let's investigate here around, so this is 55, so 52. About here is the 3 dB frequency, and the phase rotation is minus 45 degrees. And then we have a slope of minus 20 dB per decade. Here we complete the about the minus 90 degrees phase rotation of the first pole, and the first pole is of course defined as through at this internal node, at these two nodes, through the Miller compensation, R and C, and the Miller effect. And then we see that the phase rotates upwards, and this is because of the transmission zero that is set by these resistors. So the value of these resistors in this particular design point is 800 ohms. So this gives us phase margin at unity gain bandwidth which is about here. We have minus 130, which is 60 dB phase margin, and this is at a frequency of 4 gigahertz. Now it's very interesting to see the effect of the resistor. So what you can do is run parametric simulation and then literally see if you change the resistor to say 3.k multiply. So now we'll see how changing the Miller resistor can influence the transmission zero, and these are the characteristics that we got. Here it is. So you can see these are the phases for different values of the resistors, and basically what takes place is that the zero shifts because the zero depends, the transmission zero depends on the value of the resistor, and the transmission zero shifts in the frequency domain, so here in the frequency domain. And then having these graphs, you can choose the value that gives you the highest, the largest phase margin. So in this case I chose 800 ohms. So I'll go back, and then this is 800 ohms. Now let's see what is the effect of the common mode. So then I will sweep V common mode and say from 0.2 to 0.8. I remind you that the power supply is 1 volt. Say 0.05. Yeah. So now I'm changing this voltage, and then by changing this voltage I'm changing the common mode of the output signal, and for different common modes of the output signal I will run then AC simulations and investigate the body plots. So you can see now that we have somewhat different gains, because for different levels of the output common mode the transistors are at different operation mode, hence they have different GMs and R outs. Now this one is clearly not working, so when the common mode gets too high, when we have a setting of 0.8, then most probably the load, the pmos load, does not function properly, and the gain of the second stage drops, so we are only left with the gain of the first stage. So clearly 0.8 does not work. Then we have little effect in the phase, but there is still some effect for different common modes. But still, it's stable system. It's stable system, except for 0.8 volts common mode. Now, is this really so? So I will not run anymore 0.8. I will exclude it because system does not work for these voltages. And then I'll run transient. You have to validate always your design with transient simulation. Now I'll plot separately the output and the input voltage. So let's run this simulation. So first for the nominal 0.5 volts common mode, and see what I get. Here it is. So I'll also plot the input so that you can literally see the amplification. So this will be the input, and here is the input. So see the input, here it is. So this is the input voltage, and then I have about 55 dB amplification. So you can see this is there all together. See and then I will change now the common mode. So now the common mode is here for the output signal, and now I will simulate for different levels of common mode. So I'll switch off the input, and I'll be plotting only the output. So this simulation. So this is the parametric sweep of the common mode setting. Alright, now what we see here is that some of the settings are not stable settings. So you see here, let's consider only the positive inputs, and then you see here that for extremely low common modes, and here the signal is not stable. It starts sort of unstable oscillations. So when the input common mode is too low, then the nmos transistor in the second stage does not operate properly. It's out of saturation most probably. And then you see that the output is not stable. And this is something that is missed in the AC analysis simulation. You have to catch it with transient simulation, this issue. And the reason for this is that the AC simulation is linear simulation. It linearizes the transistor at certain operation mode. While the transient simulation is a nonlinear simulation. It considers the nonlinear large signal equations for the operation of the transistor. And as the output signal changes in amplitude and its common mode is very low, then the transistor gets out of saturation and changes its small signal parameters such as GM, etc. Eventually, as you can see, this leads to instability. Instability that was missed by the AC simulation, and this is the reason why we always must run transient simulations. So you see, we get stable output for common mode of 400 millivolts, and then for 400, 450 up to 750 it's stable, and we have gain. So we can just also show this. Of course, this range is also something that you can optimize for. But this is then how we change actually the. So let's highlight one 650 and here 650. So this is how we change the output common mode, and we adjust it to a level that we want. So this is it. You can further play with the parameters. So for example, the parameter of the number of fingers, it affects actually the gain, the bandwidth for sure, but the gain through the size of these sense common mode resistors. So if I increase it to 128, now the W's of all transistors increased, and what you can see is that there will be some small elevation of the DC gain. Let's see it. Not really here. You don't really see it. So it's still around 55. So perhaps it was already at certain optimum. Let's go to some extreme value, so very small W's. Then you can see that the DC gain drops. Yeah? So what happens is that these resistors here, they draw current when I have if I have signal changing in the opposite direction, there will be current flowing here, which for example needs to come from here. So this means that there will be certain W needed of the transistors, and if the W is too small, then you reduce the gain basically. So solution is, for example, here we had about 36. You can either increase these resistors very much, so let's see, increasing 10 times. Just one simulation. Yeah, so you higher it, or you increase W. But of course this will increase the power consumption. So you see now it's 53. Yeah, this is it. This is what I wanted to cover today. So thank you very much for your attention. What I showed you is a two-stage differential amplifier with input stage which is based on self-biased inverter pseudo differential inverters, and a second stage which is nmos common source amplifying transistor with pmos load as current sources, and these current sources are controlled by a common mode feedback, and through an amplifier in the common mode feedback we can set the output common mode to a level that we want. So thank you very much for your attention.